When we talked about Sn2 reaction and requirements for its successful occurrence, we mentioned that we need a good nucleophile to engage in this reaction. We also need a primary or possibly a secondary substrate for this reaction to proceed reasonably quickly. Knowing what we learned there, one would imagine that this reaction of a t-butyl bromide, so tertiary substrate, with methanol, which is a weak nucleophile, would not give us any product. However, if we heat this for a certain amount of time, what we'll start seeing is the formation of this ether and an HBr molecule. So it seems like substitution here really works. Although according to what we know about Sn2 reactions, it certainly shouldn't. Also, if we look at the rate law, what we'll see is that the rate is proportional to the concentration of the t-butyl bromide and nothing else. And this is quite unusual because in Sn2 reaction, we know that the rate is proportional to the concentration of both nucleophile and our substrate. What these two findings seem to indicate is that we have a different mechanism that is operational. So this reaction does not proceed through Sn2 mechanism. And indeed, this and similar reactions are classified as Sn1 reactions, which are also substitution reactions, but they're called nucleophilic unimolecular substitutions. So this is Sn1 stands for substitution, nucleophilic unimolecular, because only one molecule is featured in the rate law. If we think about the mechanism of this reaction, it proceeds through as a multi-step process. The first step, that is also the rate determining step, is the formation of the cation. So our t-butyl bromide simply breaks up, and this is a slow process, into t-butyl cation and bromide anion. And so this is the carbocation formation. The second step occurs quickly. Once the carbocation is already formed, the molecule of methanol, even though it's a weak nucleophile, can attack the carbocation because it's such a strongly positively charged species. And so this reaction occurs quickly to give us the so-called oxonium ion, which has a positive charge on the oxygen. And this is the actual nucleophilic attack step, which, as I said, occurs quickly. Finally, the last step is relatively simple. It's simply deprotonation of this species through interaction with another molecule of methanol. This is fast and reversible, and as a final product it gives us our ether, as we observed, and protonated molecule of methanol. So this final step is deprotonation. The important point to reiterate here is that the formation of the carbocation is the rate determining step. And it's as the rate determining, it's the slowest step in our reaction sequence, and hence it's the one that will determine the overall rate of reaction. This explains why our nucleophile is not featured in that rate equation. If you look at these relationships on an energy diagram, our first step has a high barrier. It's a rate determining step, and it gets us to high energy intermediate. This is our carbocation, starting with which is a bromide. This transition state is high in energy. But the second transition state is relatively low in energy, and so our intermediate quickly passes over it to get to the stable final product. This will be our Sn1 reaction, which has two transition states, two steps, and one intermediate. In our Sn2 mechanism, we start with the starting material, go through a single transition state, and end up with a product. This would work if we used a primary substitute such as acetyl bromide. And since both of our reactants have to participate in this one step, since it's a single-step reaction, both of them are featured in the rate equation. Now, if you think about sort of experimental observation, we got to ask ourselves a question: what does this all mean? Right? What can we observe? The first thing that we can observe is that the nucleophile doesn't matter in Sn1 reaction. Even a weak nucleophile will work. The second thing that needs to be noted is that the structure of starting material matters a lot, because its starting material is the only thing that is featured in our rate determining step. So if we have our R plus Lg, we need to get these two products, and they both have to be relatively stable for our reaction to occur at some reasonable rate. And so now we really need to talk about cations, because R plus is a cation, and see what stabilizes them. If you remember from our discussion about reacting intermediates, we noticed that one of the factors that stabilizes them is hyperconjugation, which is overlap of the empty p orbital of the cation with adjacent sigma orbitals, which make more substituted cations more stable. So our order of stability is tertiary versus better than secondary, better than primary, and then better than methyl cation. And the rate of Sn1 reaction parallels this trend. The other thing that stabilizes cations is a resonance. And we've seen that in our discussions of resonance. If we have this bromide, we have this primary bromide, this thing can lose Br minus, and even though a primary cation shouldn't be too stable, in this case we get a primary cation which is stabilized by resonance. So this electron pair can move over here and give us a different resonance structure. Since this cation is stable, either one of these two resonance forms can react with, say, water to give us our OH+, which can then easily be deprotonated to get us to our final product. And this reaction occurs on allylic or benzylic positions very quickly as well. It's important to notice that no reaction in either Sn1 or Sn2 sense will occur on aryl halides or aryl substrates or vinyl substrates. The reason why no reaction will occur in Sn2 case is because backside attack on these species is impossible, because you have to go basically through the plane of the aromatic ring or through these atoms to get there. In the Sn1 case, the reason lies in the significantly lower stability of sp2 hybridized cations versus the sp3 hybridized anions. And so this is an important point that we need to remember. If we think about the leaving group in Sn1 reaction, it has to be good. And this is the same, or analogous to the Sn2 reaction, because both reactions in the rate determining step require the leaving group to leave. And so good leaving groups are I, Br minus, water, alcohols, sulfonates, etc. Finally, when we talk about solvation, here we have the opposite effect. Unlike the Sn2 reaction, where our cations and anions were important at the beginning of the reaction, when they served as nucleophiles to attack our substrate, in this case, our cations and anions are formed at the end of the rate determining step, and so they need to be stabilized. And so solvation is favorable since it can stabilize R plus and Lg minus. At the same time, it will destabilize the nucleophile, but that doesn't matter much since, well, it will not destabilize the nucleophile. It will make the nucleophile less active, but it doesn't matter much because we don't really need overly active nucleophile for Sn1 reactions. They will go anyway. Okay? And so in this case, polar Protic solvents are best. Polar Protic solvents are those that are capable of hydrogen bonding, such as water, ethanol, even acetic acid will be a good solvent for these reactions because they will stabilize our leaving group during the course of the reaction. Now, the fact that the Sn1 reactions proceed through carbocations leads to several important features of these reactions, which we will discuss in the next two subslides.